This is Algebra 2, Lesson 6-1, Roots and Radical Expressions. A radicand is the number under the radical sign. A radical sign could be a square root, a cube root, a fifth root, a 12th root, whatever. But a radicand would be something like, this is the 12th root of 1056. The radicand is 1056. The index gives the degree of the root. So the index number here would be 12. In this particular thing, this is the index. And the principal root is the positive root of a number when it has two real roots. Okay. In Chapter 5, we used root to represent the solution of an equation. For example, 2 is a root of the equation x to the third equals 8. For such a simple power equation, you can simply refer to 2 as the cube root of 8. Okay. So, essentially, we have this. Since 5 squared equals 25, 5 is a square root of 25. 5 cubed equals 125, so 5 is a cube root of 125. 5 to the fourth equals 625, so 5 is a fourth root of 625. And 5 to the fifth is 3,125, so 5 is a fifth root of 3,125. This basically leads us to what we call the nth root. If a to the n equals b, and a and b are real numbers, and n is a positive integer, not a negative integer, then a is an nth root of b. Now, if your nth root is odd, there is only one real nth root of b, denoted in the radical form as the nth root of b. However, if n is even, like a square root, a fourth root, a sixth root, an eighth root, etc., there are two real nth roots of b. The positive root is the principal root, or the principal n root, and its symbol is the nth root of b. And the negative root is its opposite, or the negative nth root of b. For example, the square root of 25 is both 5 and negative 5. It has two roots. 5 is the principal square root. Negative 5 is not the principal square root. Okay? If b is negative, there is no real nth root of b. We've already talked about that because then you get into the imaginary number system. Okay? And the only nth root of 0 is 0. Okay, so when we're finding roots, we're going to find all the real fifth roots of 0, negative 1, and 32. Real fifth roots, which means no imaginary numbers. Okay, so we're thinking about the fifth root of 0, which basically means this. We're taking the fifth root of 0, which happens to be 0. The fifth root of negative 1, since negative 1, the only way to keep it negative is the root has to be an odd number. Therefore, there is a real root of negative 1, but there's a real fifth root of negative 1, and it's negative 1, because negative 1 times negative 1 times negative 1 times negative 1 times negative 1 is still negative 1. And then we have the fifth root of 32, which means now you're going to break this down. Now you're going to take 32 and you're going to break it down to 2 times 16, which would be 2 times 8, which is 2 times 4, which is 2 times 2. So you have 1, 2, 3, 4, 5. You have to have 5 roots, 5 of the same thing to take it out because your index number is a 5. Remember when we had square roots, we had to take out things in groups of 2? Well, now that we have fifth roots, we have to take out things in groups of 5. If it was a 12th root, we have to take out things in groups of 12. So the fifth root of 32 is 2. So the fifth root of 0 is 0, the fifth root of negative 1 is negative 1, and the fifth root of 32 is 2. Okay, what are the real square roots of negative 0.81, 25, 49, and 121? Okay, square roots now. So we're looking at the square root of negative 0.81. Well, there are no real square roots of a negative number. It's an imaginary number, so there's none here. Okay, we're looking at the square root of 25 49ths. Remember, we can rewrite this as the square root of 25 over the square root of 49. Square root of 25 is 5. Square root of 49 is 7. However, okay, it didn't ask for just the principal square roots. Okay, so we have 5 sevenths and we have negative 5 sevenths because we have two real roots of an even numbered index. And the real roots of 121. The square root of 121 is 11, but we have to have both the positive and the negative, because there are two roots of your even indexes. Now, according to the fundamental theorem of algebra, which we learned last chapter, right, x to the fourth minus 1 equals 0 has 4 roots, only 2 of which is real. In this chapter, the focus is on the real roots only, so we're not going to have to worry about the complex roots or the irrational roots. We're just basically talking about your real roots. All right, so find each real numbered root. We're going to find each real numbered root here. So again, remember, you have to look at your index number, okay, because that tells you how many you have to group up to take something out. And some of you may know your cube roots and your fourth roots and your square roots really well, but after a while, you probably do not know like your 12th roots. I don't. I have to actually look them out. So the cube root of -8, I know that 2 to the third is 8. So -2 to the third would be -8. So this is going to be -2. Because -2 times -2 times -2 does equal -8. The square root of -100, there's no real root. Because it would have to be an imaginary number, because the square root of a negative number is the I. Okay. The cube root of -27. Well, remember, -27 is -3 times +9. Okay, and 9 can be -3 times -3. So it ends up to be -3. And how do I know it's negative? Well, if it's an odd numbered root, 3, 5, 7, 9, I know I'm going to have to take out a negative number in order to make that root work and stay negative. And the fourth root of 81. Well, 81 is 9 times 9. And 9 is 3 times 3. And this 9 is 3 times 3. We need to take out groups of 4. Here we took out groups of 3. So here we have to take out groups of 4. So the real root here would be 3. Okay. All right. Now, it is very tempting to conclude that the nth root of a to the n is a for all real number a. But if n is even, the nth root of a to the n is positive, even if a itself is negative. This is really, really important. And this is probably the most confusing thing that people have when they deal with simplifying roots. The nth root of nth powers, for any real number a to the nth root of a to the n is a if n is odd. So if it's a cube root, it's just a. If it's even, you have to take that a and put it in the absolute value symbol because you don't want to accidentally introduce a negative. Okay? It's easy to overlook this rule because you just don't think about it all that much. It is particularly important, however, that you remember it when the radicand contains a variable expression. It doesn't matter when it does not matter when it has a numerical expression. It does matter when it has a variable expression. You must include the absolute value when n is even, and you must omit it when n is odd. An easy way to remember this, okay, is to include absolute value symbols when you take an odd number of variables out of an even numbered root. That's the easiest way to do it. Because if you take an even numbered variable out, if you square a negative number, it still stays positive. Okay. Essentially, this is what this means. Now let's take a look at this. If I have the square root of 4x to the 6th, 4 is 2 squared, and x to the 6th is like saying x to the 3rd squared. Okay, so it's like saying the square root of 2x to the 3rd quantity squared. Well, we know that the square root out here, the index out here, cancels out that right there. 2 is 2 no matter what. However, I'm taking an odd number of variables out. I'm taking an odd number of variables out of an even numbered root. I don't want to accidentally introduce a negative, because notice there's no negative numbers underneath the radical sign because it would be a non-real root. Therefore, I have to put the x in the absolute value symbol. Okay? The index number is even, so the absolute value symbol is essential. Okay? Your index is even, so absolute value is essential. Because I took an odd number of variables out of an even numbered root. Okay. Let's look at this next one. The cube root of a to the 3rd b to the 6th. Well, that's like saying the cube root of a to the 3rd times b squared to the 3rd power, which is the same thing as saying the cube root of the quantity ab squared all to the 3rd power. Okay, which means this, again, cancels out this. So I get ab squared. Why do I not need absolute value symbols here? Because it's an odd index number. Okay? Odd index number. So you must not use. Okay? If you do put in the absolute value symbols, it'll be wrong. Okay? You do not need the absolute value symbols because you can have a negative cube root. You can't have a negative square root. Okay? If you use an absolute value symbol where it's not needed, it's wrong. If you don't use an absolute value symbol where it is needed, it's wrong. So it's really important that you pay attention to those absolute value symbols. Let's look at one more example here. The fourth root of x to the fourth, y to the eighth. That's the same thing as saying the fourth root of x to the fourth, y squared to the fourth. So quantity x, y squared to the fourth. Since it's a fourth root, okay, we need 4 to take out 1, don't we? We have 4 x's, so we take out 1x, but we take out y squared. Notice, the y squared doesn't need to be in the absolute value symbol. Okay? Because no matter what, it's not needed because when you square y, even if it was negative, it would turn into a positive, wouldn't it? Because y squared is negative, never negative, because negative 1 squared is positive 1. Okay? So here, because we took an odd number of variables out of an even numbered root, okay? Odd number of variables out of an even numbered root, we need the absolute value on the x only. Okay. Now you might go back up to problem 1 over here. Sometimes I've seen problem 1 written this way. I've seen people write it 2x squared absolute value x. To me, that's the same thing as 2 absolute value x to the third. This 2 absolute value x to the third is much cleaner, so we tend not to separate them. Okay? If you take an odd number out, just leave the whole odd number in the absolute value symbol. It's really easy to remember. If you take an odd number of variables out of an even numbered root, I took 1 variable out of a fourth root. That's odd. This is odd. This is even. This is even, so I didn't have to do anything with it. All right, so let's practice this. Now that I've shown you how it works, let's actually do it. So we're going to simplify each radical expression, and we're going to use absolute value symbols where needed. So we have the square root of 4x squared y to the fourth. Since the root is 2, it's not expressed, but the root is 2. So you need 2 to take anything out. Well, I know that 4 is 2 times 2, so I can take that out. Now, I don't want to have to go x times x and y times y times y times y and circle them like this. You can, if you wanted to, but think of it this way. The easiest way to think about it, if it's x squared, okay, this is going to be divided by the index number. So I can take out 1. Y to the fourth is going to be 4 divided by the index number, so I can take out 2. Same thing as I showed right up here, isn't it? So I have 2. I took an odd number of x's out, so that's the absolute value of x. I took an even number of y's out, so y squared. So 2 absolute value of x, y squared. And you still leave the variables in alphabetical order. Now we have a cube root, negative 27x to the 6th. Right? The cube root of negative 27 is negative 3, because negative 3 times negative 3 times negative 3. Remember, c to the 6 is going to be 6 divided by 3, so I can take out 2 of them. So I have negative 3c squared. And there we have the answer to B. Letter C here is the fourth root. There's no numbers, just variables. So I think of this as x to the 8 is going to be 8 divided by 4, so I can take out 2. Y to the 12 is going to be 12 divided by 4, so I can take out 3. So I can take out an x squared, which does not need absolute value symbols because I took an even number out of an even numbered root. But the y to the third does because I took an odd number of variables out of an even numbered root. It's not a hard concept once you get your mind wrapped around the odd out of even thing. Okay, it's the easiest way to explain it. All right. Using a radical expression, let's say we have a citrus grower. He wants to ship a select grade of oranges that weigh from 8 to 9 ounces in gift cartons. It's Christmas time. Everybody loves to give fruit at Christmas. Each carton will hold 3 dozen oranges in layers of 3. Excuse me, in 3 layers of 3 oranges by 4 oranges. Okay? The weight of an orange is related to its diameter by the formula W equals D to the third divided by 4, where D is the diameter in inches and W is the weight in ounces. Cartons can be ordered in whole inch dimensions. So what size cartons should the grower order? Let's face it, he grows the oranges. He might package them and ship them, but he has to order the cartons from somebody else who creates the cartons. Okay, so first thing we need to do is we need to find the dimensions of the orange. Okay, so we're going to find our dimensions of our orange. Because that's going to tell us what size cartons we need. Okay, so let's think about it. The weight can be between 8 and 9 ounces. It said that. Okay, right up here. Okay, so the weight is between 8 and 9 ounces. Oops, I can spell. Let's spell that better. Okay, so already I know that if I let W equal weight, I can write an inequality here. Okay, so the weight of my oranges is between, so it's greater than or equal to 8, but less than or equal to 9. Okay, now my weight, if you remember, is found by the formula, see, W equals D to the third over 4. So now I'm going to substitute this in for this. Okay, so now I'm going to say 8 is less than or equal to D to the third divided by 4, which is less than or equal to 9. Now I have to solve this inequality. So my first step is to multiply both sides by 4. I multiply everything by 4. I multiply this by 4, multiply this by 4, multiply this by 4. These two 4's cancel out, leaving me with D to the third. Where 8 times 4 is 32. 9 times 4 is 36. Okay. So now, in order to solve for D, I have to take the cube root of everything. Okay. And of course, I'm going to have to use my calculator because those are not perfect cubes. So if I stick the cube root of 32 on my calculator, I get approximately 3.17, which is less than or equal to D, which is less than or equal to the, or excuse me, the cube root of 36 is 3.30, approximately. It's not exact, but it's really, really close. Okay. So, remember what we said. Okay, we now know that the diameter of the oranges is between 3.17 inches and 3.30 inches. Remember that they're going to ship, okay? Cartons can be ordered in whole inch sizes, but he's going to ship them in 3 layers of 3 oranges by 4 oranges. Okay, 3 oranges by 4 oranges. So think about that. He's going to have a carton over here that's 4 by 3 this way, or doesn't really matter. 3 oranges by 4 oranges. It doesn't really matter which way you orient the cart. It's basically a carton. It's going to basically look like that. Okay, so we probably should order our cartons based upon the largest orange, because if you order them based upon the largest orange, you know the smaller orange will fit in it. So if I say I have a row, okay, that is 4 oranges long, that's going to be 4 times 3.30, which is 13.2 inches. And then I have a row of 3 oranges, which is 3 times 3.30, which is going to be 9.9 inches. Okay. Now remember, it says that the grower can order cartons in whole inch dimensions. Okay, that would be this right here. Okay, all these things we have to pay attention to. Whole inch dimensions. So if I go back down here, whole inch dimensions, I'm going to have to go up for this one and up for this one as well. So you should order cartons that are 14 inches by 10 inches. Okay? Because if he orders them to accommodate the largest oranges, he knows he can accommodate the smaller oranges. So there you go. That's the application of some radicals.